Okay, so once again, good evening and welcome you all to this online interactive lecture series that we have been organizing on behalf of the INO project for many weeks. In fact, today is the 33rd talk in this series, which, as I said, are going on for more than 10, 12 weeks. And the talk today is titled as The Particles Predicted by Theory. It's going to be delivered by Professor Sunil Mukhi, who is the Dean of Faculty at IISER, Pune. Professor Sunil Mukhi obtained PhD in theoretical physics from Stony Brook University in 1981, and his research specialization is elementary particle physics with a focus on fundamental aspects of quantum field theory, gravitation, and string theory. After working at the TIFR, Tata Institute of Fundamental Research, Mumbai for over 27 years, he moved of late to the Indian Institute of Science Education and Research, that is IISER, what I said, Pune, in 2012, to engage in pedagogy at a larger scale. So he has taken year-long sabbaticals, one at CERN, Geneva, and then the Institute for Advanced Study, Princeton, and has been a visiting fellow commoner at Trinity College, Cambridge. He's a fellow of the Indian Academy of Sciences, the Indian National Science Academy, and also the World Academy of Sciences. And he received the Government of India's Shant Swarup Bhatnagar Prize in Physical Sciences way back in 1999. And he has been an editor of the Journal of High Energy Physics, the leading journal in the field, since its very inception way back in 1997. So with those few words, I now request Sunil Mukhi to start his lecture.
Thank you so much, Satya. I hope everyone can hear me well. It's a real pleasure to be giving this talk. I really want to express my appreciation to Satya particularly and all the INO people. Of course, my wish is that the INO project goes forward smoothly. It's had many hurdles, but it's very important for our country that such projects actually get carried out. And last, I want to just give a little bit of a disclaimer. I'm not that much of a historian, but this is a historical lecture. And my goal in giving it was to put together a few things which are normally discussed separately. So I think that is my only contribution, that maybe in one talk, I'm trying to give a perspective on many different discoveries, but only not focusing on, the whole particle physics or how the subject developed or anything like that. But assuming that you have, I know all of you students have read a lot on your own. And what I'll do is just to give some perspective on certain cases where theory predicted elementary particles. And one reason I like to do this is because physicists who are not in particle physics field don't really appreciate the fact that this can even happen. The fact that a theory can predict a new particle never seen by an experiment is rather special to particle physics, in my opinion. It can predict a new phenomenon, even at the level of existence of an object. Usually, theory predicts, one more behavior of some system, of some material or something. But here it actually has predicted the existence of particles, some elementary, some composite, and I'll try to take you through the history of that. If you have questions, you can type them in the chat at any time, and I'll also pause from time to time for questions. So, and also the talk is, of course, going to be very elementary from the technical standpoint, but of course, I'll touch upon many topics which really require a lot of study to understand in depth. So with that, let me start. So, the 20th century was an era of new discoveries in particle physics that will perhaps never be matched again, because these are dangerous statements, but still. In every, in almost every decade of that 20th century, there was, something or other, some kind of ferment or other, particularly until the mid-70s. Then discoveries slowed down after that, but still there were some important ones. So in this century, or in that century, atomic structure was understood, and that led to the creation of subatomic physics and then subnuclear physics. So actually going even into the nucleus, and well, they are often discussed in the same breath. And today we call this field particle physics. Now, the most crucial role in why we could do this in the 20th century was not because there were brilliant people. Every century had brilliant people, but the 20th century had new experimental techniques for production and detection of objects at higher energies, with higher resolution, with more powerful magnets, with more powerful more techniques for accelerators. And it was these new techniques that played by far the most crucial role. During the same century, on the theoretical side, several revolutions took place, and three of them are noteworthy because they all took place in the early part of the 20th century, long before any of us was born, I think. And they are quantum mechanics, special relativity, and general relativity. It's quite remarkable also that Einstein participated in all of them, but the two relativities were sort of his thing. Quantum mechanics was much more of a group effort and involved some back and forth between different types of people in different places. Now, the resulting theories that came out of these revolutions, they give us strong constraints on what is possible in nature. And this is a funny statement, which I'll try to emphasize and explain again and again during this talk. But let me just say that this is particularly so if we use both quantum mechanics and special relativity. And this is what we must use if the systems are very microscopic, so quantum mechanics is needed, and also objects are moving at speeds close to the speed of light, so special relativity is also needed. It turns out that QM plus SR is a highly constrained theoretical system, and within that system, it's not possible to play with little pieces of it. You can imagine a kind of house built of blocks. If you pull out one block, the entire house collapses. It's a bit like that. It's one constrained system, and everything has to work as it works. And we don't get to change the rules very easily. That's very important. Now, these kind of tight constraints, which include things like symmetries, conservation laws, consistency conditions of other types, led to theoretical predictions of several particles. And let me list the ones that I'll talk about in this talk: the positron, the neutrino, the Eta meson and the Omega baryon, quarks, W bosons, Z boson, and the Higgs boson. Okay, so these are if you count them all, there are 8 objects here. But of course, there are many quarks, actually. There are many neutrinos. There are many antiparticles. So it's not so simple. But for my talk, this is going to be what I'll discuss. There are also things I won't discuss. Yukawa's prediction of mesons. There was a prediction of gluons. There was a prediction of charmed quarks by theoreticians. And these all are very nice. If I had one more hour, I could probably tell you about them. But to make a little story which is concrete, I'll stick to the ones in my main list. Okay, and let me start right away. So the positron. Now in quantum mechanics, we use a wave function called the Schrödinger equation to describe the wave function of particles. Most of you have seen it. This is what it looks like in his own paper. So I just took the liberty to copy and paste it. This is the time-independent Schrödinger equation from Schrödinger's own paper on the subject. And it's a very good equation. It's still used. It's widely used. It can be generalized to many body systems, but it's not compatible with the special theory of relativity. And the reason is this first term over here. This is the Laplacian in 3 dimensions. So if you go to a different frame of reference, this equation will change its form. And that's not what special relativity allows. It says equations must have the same form in all frames of reference. So it was in 1928, somewhat after this equation, that Dirac proposed a wave equation to describe the electron in a relativistic situation. So for relativistic electrons, and he deliberately set out to find an equation that would be quantum mechanical and also compatible with special relativity. And here's the title of the paper, The Quantum Theory of the Electron. From today's point of view, looks a bit immodest. It seemed to solve everything. Actually, it was really the beginning, but it was a very, very important beginning. Let me also show you a photo of Dirac, which I've seen a few times, and it's worth showing because this is Dirac in India, in Kolkata actually, with Dr. Purnima Sinha, who was the first PhD in physics from Calcutta University. And I'm not sure if he came to India more than once, but certainly this is from his visit to Calcutta. Okay, and Dirac wrote, in his notation, wrote an equation which looked like this, which has some momenta, P0 and 3 momentum here. So this is energy and 3 momentum. And then some matrices, sigma, the Pauli matrices, in fact. And this is Dirac's equation in its simplest form. It's the free Dirac equation. It's nowadays written in a more abstract form, but this is basically what it is. And here's the mass of the particle. Here's the speed of light. So it's what you expect from a relativistic wave equation. Now, this equation, when analyzed, predicted 2 types of quantum states. It predicted states with positive energy, which could be identified with electron states. And it also predicted negative energy states, which was a bit of a puzzle. And the puzzle actually lasted for a few years. And Dirac actually went down a wrong direction before he realized what the puzzle indicated. So here's a schematic picture. It's only schematic. The X's are like quantum states. You can think of them as being unoccupied quantum states. And then if I have an electron, I can just put it into any of these states. If I put it in the part above this dividing line, over here, then it'll have positive energy like this. And if I put it in any of these, then it'll have negative energy, which is a very strange thing. It's not only strange, but this thing goes down forever. So you could imagine creating states of more and more negative energy, which sounds really very disturbing in physics. Now, your first inclination might be, let's ignore these negative energy states. And Dirac pointed out that, well, it's not that simple, because whenever you have quantum states, a particle can jump into that state by a transition. You can't really insist that it's not allowed to do that. So one has to find some explanation of those states because of this reason, especially in a quantum theory. And Dirac proposed that these negative energy states are already filled. By the Pauli exclusion principle, we just fill them all, and we assume that nature gave us empty space, vacuum, in which these negative energy states are already filled. We don't ask why, we just do it. The good thing is, because of Pauli exclusion principle, we can actually do it, or we can imagine doing it. Okay, so the circles are filled states, the X's are empty states. Now, the only states you can populate are the ones above this axis. So those are positive energy states. Okay. Now an electron can make a transition into a positive energy state from this negative energy C, which was called the Dirac C, leaving behind the hole. And the picture is like this. So if you see my cursor, there was an electron here filling the C. It's gone here. So now this new system, or this new state, has an electron here, but it also has a missing electron here. So it has 2 things, and both of them can travel. This one can travel around in position or in energy. This hole can also travel. So Dirac said, well, the hole behaves like a positively charged particle because it's the absence of an electron. And so we'll call it an anti-electron. And in nature, experimentalists will see it as an independent elementary particle. And it eventually got the name positron. So Dirac went down a wrong direction, where he thought actually that this hole was a proton, and he wrote a paper on that. And it was Oppenheimer who convinced him that, look, it cannot be the proton for 2 reasons. One is that if the proton is an anti-electron, then they can annihilate each other and the hydrogen atom will go poof, which is really not a good idea at all. Secondly, the antiparticle should have the same mass as the particle. And so after 3 years, in fact, Dirac came to the conclusion that there must be a new particle called the anti-electron. I think that's what he called it, which corresponds to these holes. Now, electrons and positrons are created together. It's visible from this picture because the moment an electron moves from here to there, we now have an electron with positive energy, and we now have a hole with also positive energy because it's the absence of an electron in a negative energy state. So double negative, so it also has positive energy. So two particles created together in a pair. They can also annihilate by this one popping back down, and in that process the electron vanishes, the hole also vanishes, and we are back in the vacuum. So that was sort of the idea. Okay, now it sounds like a mathematical fantasy. All this was done by manipulating some matrices and some quantum operators. It was not done by asking any experimentalist what they thought. And people did find it quite a fantasy. Even Niels Bohr didn't like the idea. Niels Bohr didn't like any idea, actually. I'll come back to that. But in fact, in 1932, 4 years after the Dirac equation and 1 year after Dirac wrote a paper saying, look, there should be anti-electrons, Carl Anderson found exactly that, a positively charged particle with the same mass as the electron. And now we know many other forms of antiparticles or antimatter, such as anti-muon, anti-quark, anti-neutrino. There are even anti-protons. There's anti of almost everything, except in a few cases where the antiparticle is the same as the particle. And here's a picture of Wilson's cloud chamber. And here, if I understand right, the red is the track that a particle would leave if it was an electron. It would curve in a magnetic field. But being a positron, it curves oppositely in the same field. And that's what marks it out to be a positively charged particle. And because the shape is the same, it has the same mass as the electron. Good. So that's our first particle predicted by theory. Let's move on to the second. Maybe after the second, I'll pause for a few questions. Good. So the neutrino, of course, this entire series is about neutrinos. This one I can probably cover briefly. I think all the students here and certainly all the faculty know this very well. So the story is that in radioactive beta decay, a nucleus was seen to decay into a different nucleus by emitting an electron. Now, the emitted electron has a spectrum or a range of energies. And this is what the experimentalists find. They have no prejudice what is going on. They simply say, well, there's a charged particle coming out from a nucleus. And this is, if we take a lot of data and plot all the points, which are the red dots, and then join them, we get a spectrum or a curve of possible kinetic energies of electrons peaking at some point and then slowly eventually going down to zero. Now, unfortunately, this fact itself has a contradiction. Energy and momentum conservation tell us that if an object emits two particles, then both the energy and the momentum of those particles are fixed. Roughly, you can think of it this way. If the initial nucleus is at rest, then in that frame, it will give off two particles back to back. So they have to have the same momentum because there was no momentum to start with. But now the sum of their energies should be the energy of the original particle, which is its mass. That's two conserved quantities. If you use those, you can eliminate everything and you can find the exact momentum and energy that should be carried away by the electron or the beta particle. And therefore, in this plot, you should have found that at one value, there's a fixed number. All the data points are at one value. They're not scattered like this, but they're all lined up at exactly the same value. That's not what you find. So either energy and momentum are not conserved, or there's an extra particle being emitted, which we did not see. In the second case, the problem is solved because now if you do energy momentum conservation, the electron or beta particle and this extra particle, they can share energy. So every event can have a different electron energy and a different energy for that emitted particle, such that the total of those two is fixed. Okay, but since we don't see the other particle, therefore the electron will exhibit a spectrum of energies. So that these are two possibilities. Which one should we do? Give up energy momentum conservation or postulate an entirely new particle? Now, I know it's a bad joke, but in this social media era, what we should probably do is put this on some TV channel and ask everyone to tweet or send a message saying upvote or downvote. And I can quite imagine that if we really did that, a lot of people would vote for giving up energy momentum conservation. And these would be the irresponsible people, which we also see on social media all the time, because you can't give up something which has an enormous number of ramifications. It's not only this experiment, it's every one of all experiments done before that, which would be, the explanation would be completely ruined if we gave up energy momentum conservation. We don't give up principles that have worked very well in many contexts. This is an example of what I told you. If we pulled out this block of energy momentum conservation, then the house of all our understanding of physics would collapse. Okay. And the point here is that it's not a small amount of energy that we would have to not conserve. For this electron to have such a wide range of energies, we would have to give it up in a big way. Okay, so if we assumed that energy and momentum are not conserved, there should be many more processes that violate them, and we don't see any. So this thinking led Pauli to propose that there's a new particle being produced. We just haven't seen it. It's called the neutrino. Apart from energy conservation, he also cited the exchange theorem of statistics, which in modern language is the fact that this neutrino and electron together carry away total integer amount of spin, because both are half integer spin particles, or both are fermions. Without that, we would be in trouble with statistics, with Fermi statistics. Now, Pauli wrote, so far I dare not publish anything about this idea. He said many interesting things about this idea. He was really quite nervous. And, Pauli being nervous, for those who in this audience who possibly knew him or certainly know about him, he was the last person to be nervous about anything. And he also wrote this slightly humorous letter, which I've reprinted for you. It starts, "Dear radioactive ladies and gentlemen." This is a kind of Pauli joke. And the whole letter is written in a slightly apologetic and humorous way, saying, I'm sending you a person to defend this crazy theory of mine, that kind of thing. And the crazy theory was that there's a new particle being produced in beta decay. He also said, I have done something very bad today by proposing a particle that cannot be detected. It is something no theorist should ever do. Now, soon after that, Enrico Fermi gave a theoretical picture of the process. He said, look, the process is being seen in nuclei, but actually it's the neutron in the nucleus which is doing the decay, and the nucleus with a neutron is changing into the same nucleus with the neutron replaced by a proton. The electron is the beta particle, and this neutrino, today we call it antineutrino, is being given off. This is Pauli's object. Okay. Well, his paper came back from Nature, the most prestigious journal, rejected, saying the manuscript contains speculations too remote from reality to be of interest to the reader. Okay. This was, of course, one of the greatest contributions to theoretical understanding of the whole 20th century, but Nature referee thought otherwise. Okay. Good. Now, cut to many years later. Let's remember when all this happened. I told you in 1931, Pauli proposed this new particle, and it was in 1956 that the famous experiment of Reines and Cohen detected neutrino, and they would have both got the Nobel Prize, but Cohen unfortunately passed away, so Reines got the prize, shared with another person for a different experiment. And it remains true till 2020 that no experiment has ever found any convincing evidence that energy or momentum conservation are violated. On the contrary, we found many more neutrinos. So that's my very, very short summary of the prediction of a neutrino. So I can pause at this point for any short questions if you have.
Okay, Sunil, already there are a few questions.
Okay.
So can I request those who are on the Zoom could always raise your hand and ask questions directly. And I do see Aditya and Sadaf have typed in some message.
Yeah.
So should I read that for you?
No, I can see them. So I'll answer Aditya's question. It's quite brief.
Okay.
So he says, what does it physically mean to keep on lowering? Oh, there's also, I think Sadaf has answered it. Okay. Yeah, good. I mean, there's a question and anti-question pair. I think they have annihilated each other. But Aditya wants to know about observability of the sea. I think this is quite important. Today, I would say that I don't believe Dirac's the Dirac sea explanation, and I don't also need it. The point is that in quantum field theory, there's a completely different way we understand the vacuum. We don't have some kind of vacuum, multi-particle vacuum, and then occupy the states. Rather, we have a field which can create or destroy particles. And in today's language, the positive energy solutions of Dirac equation are the creation operators of an electron and the destruction operators of a positron, while the negative energy solutions of Dirac equation are the creation operators of a positron and destruction operators of an electron. It's a long sentence, but it's a different interpretation, and I think it's much better because it also applies to bosons, while Dirac's explanation only worked for fermions. So I won't say it was perfect. So you could argue, somebody could have told Dirac, look, wait for quantum field theory to come along. Your negative energy states will be solved. But as it happens, he made the prediction and it was confirmed. And what can I say? So don't take the Dirac sea too seriously. It's a very beautiful concept. It's even used in condensed matter physics, but it's not maybe the optimal way to understand antiparticles anymore. In modern language, antiparticles are quantum fields whose Hermitian conjugate is not equal to the original field. That's all.
Okay, that's great. One question, if I can ask from YouTube participant Sadasiv Shahu. It says, I heard Homi Baba also worked in direction of search for antiparticles, in quotes, positron, in cosmic ray flux, but couldn't point out as Anderson did. If this story is correct, then what he lacked?
Oh, I'm not aware of Bhabha. Well, I don't know. Rajaji can correct me. I'm not aware that Bhabha tried to do any experiment connected with antiparticles. Is that the case? I know what Bhabha did, of course, was to calculate the process, the scattering cross section for a process where electrons and positrons scatter off each other. And what he realized was that they can scatter by exchanging a photon, but they could also annihilate into a photon and then recreate as an electron-positron pair. And you have to sum the amplitude of both processes to get the correct answer. And therefore, the process of electron-positron scattering is called Bhabha scattering. It's obvious that Bhabha, in interaction with Dirac, being in Cambridge and so on, inspired him to think about this problem. Also, his advisor was Fowler, who is the person who communicated Dirac's original paper to the Royal Society. But Rajaji, you have something to add?
Yeah, I can add one thing to what you said. Baba, by analyzing the penetrating power of cosmic rays, he showed the existence of a penetrating component which can come only from a particle which is about 200 times as massive as electron. He called it the heavy electron. Later, the same Carl Anderson who discovered the positron discovered saw the crack in cosmic rays. So usually people say Carl Anderson discovered it, but it was actually predicted by Baba by a phenomenological analysis of cosmic rays.
This is the muon you're talking about,
Muon.
right?
Yeah. He called it heavy electron.
Heavy electron. Yeah, not the positron.
No, positron. Muon was sort of predicted by Baba.
Okay, thank you so much.
Do you also see, Sunil, a query from Amog?
Let me see. Amog, yes. In classical physics, also we come across negative energies. So why was negative solution? No, in classical physics, actually, we don't come across any system which has infinitely many unbounded negative energies. If we did, it would mean that a ball or something rolling in or a harmonic oscillator would just roll down the potential till it reached minus infinity, which is physically absurd. So no classical system has energy unbounded below. If it's just finite and negative, it doesn't matter because you can redefine the zero of energy. But in this system, there were all negative energies down to minus infinity. That means unlimited negative energy. That's completely different. Okay, I think with that, I'll move on.
Can I
Yeah,
add
there-
something? Can I
Please,
add
yeah.
something, please?
Yeah,
Can I add something to what Sunil said?
please go ahead. Go ahead.
You see, in classical physics, there are no quantum jumps. So you can simply ignore all the negative energy solutions because there is a gap between negative energy and positive energy. But in quantum mechanics, we cannot do. That is the reason why in quantum mechanics, only the same, you see, because Einstein's equation, which is equal to E squared equal to P squared, C squared plus M squared, C power 4, gives you plus or minus both, because it is a square root. Plus or minus both will come in classical mechanics also, classical relativistic mechanics. But there, the trouble does not come because we simply ignore the minus sign. But in quantum mechanics, it cannot be ignored because of quantum jumps.
Of course, there's no gap for massless particles.
Yeah, but all the particles are massive. So there is a gap, and
I think in modern language, E is always plus square root of P squared plus M squared. And that's it.
in classical physics.
No, I think in all physics, even in quantum physics, E is just square root of.
Is there. That is why Dirac equation predicts negative energies also.
Yeah.
Anyway.
Okay.
Okay.
Okay. So I'll go on now.
Yeah.
So now we come to the 1950s. So during the 1950s, many strongly interacting particles called hadrons were being discovered. And that's in large part, as I said in the beginning, due to the development of newer and better accelerators. And these particles were coming in huge profusion. I mean, literally dozens at a time. And it was not clear if they were elementary or composite. Today we know that they are not elementary particles, Eta and Omega. They are not in any list of elementary particles. But they were being produced. They had never been seen before, and they had to be classified and explained. Now, some of them had half-integer spin, and they were similar in mass, in the ballpark of mass, to protons and neutrons. That's about 1 GeV, 1000 MeV. And these were called baryons. Others had integer spin, so 0, 1, 2. The first set had half, 3 half, and so on. Second set had 0, 1, 2. They were more similar to pions, whose mass is in the 150 MeV range, which are seen in cosmic rays. So many more such particles, pion-like, were seen, and those were called mesons. Okay, the mu meson turned out to be a wrong name, and that name was dropped eventually. So that's not a meson in our language. But strongly interacting particles which were found were either baryons or mesons. Now, there was this embarrassing profusion of particles, and people hate that because, particle physics is not about making huge lists of particles and memorizing them. It's always about finding the reason for things. And many people tried, including even before 1961. I'm skipping over that part of the story because just because of time and because this is the prediction that was successful ultimately. In 1961, Murray Gell-Mann, who you see here, and independently Yuval Ne'eman, proposed a classification scheme where they said, look, there is some mathematics into which I can fit all these discoveries of baryons and mesons. And it was a mathematics which today many particle physicists, all particle physicists know quite well, but in 1961, no one really knew it except these people. Now, what is SU3? So that was the basic concept. So it's a mathematical object called a Lie algebra or a Lie group. It's really the Lie algebra which appears here. And it's if you like, it's a set of infinitesimal transformations, but it works in some strange three-dimensional complex space, which we are not used to. The space we are used to is the space of physical rotations. And it turns out that a simpler version, a simpler Lie algebra called SU2 describes rotations in ordinary space, but SU3 is distinctly more complicated. Now, all Lie algebras have representations which are some mathematical vector spaces in which the symmetries act, and they have some fixed dimension. And if you want to know the dimension of the irreducible representations of a Lie algebra, you have to open the classic works of mathematicians, which also were only done in the 19th and 20th centuries. It's not such an old subject of mathematics. And in particular, Gell-Mann wrote this paper, which was actually more like a preprint than a paper, The Eightfold Way, a Theory of Strong Interaction, Symmetry. And Neyman wrote another paper independently in the same period. And this is not a published paper. This is actually sort of an internal report from Caltech. And what it contained was the following observation, that baryons and mesons, the ones being found by experimentalists, appear to follow the mathematical rules associated to this Lie algebra called SU3. And here is an illustration. So the Lie algebra SU3 has a famous representation which is 8-dimensional, but mathematicians don't write the 8-dimensional representation as a column vector with 8 entries. They write it as a hexagon with 2 dots in the middle. So you see 1, 2, 3, 4, 5, 6, and 7, 8. And mathematicians have a name for these. I couldn't find in time a diagram from a mathematics book, but you can easily find it. So these points are called roots, the 6 points here, and these 2 points are called Cartan generators. So there's a distinction between 6 of them and another 2 of them. Okay. What Gell-Mann and Neyman did was to take this same diagram of a hexagon with 2 dots in the middle and say, well, how nice. We can fit the known baryons that are being discovered. Well, here are neutron and proton. For context, these of course were known since a long time. But sigma minus, sigma 0, sigma plus, psi minus, psi 0, and lambda all fit into this diagram beautifully with some property which is associated to the axes in a slanted way, as I've shown down here, exactly what mathematicians do when they discuss the 8-dimensional representation of SU3. In particular, a quantum number called strangeness acts this way. So the strangeness of these is 0. That's why they were first to be discovered. These have minus 1 unit of strangeness. These have minus 2. It's a conserved quantum number in particle interactions. Not exactly conserved, but at that time it was thought so. Q is the electric charge, and it goes diagonally like that. So this line has Q minus 1, electric charge minus 1. Here you have, oops, I did something. Yeah. Here you have the neutron, the sigma 0 and psi 0 all neutral, and here you have positively charged particles. And all these particles have masses that are not so far apart. They are between 938 and about 1400 MeV. So these two people proposed that there's a symmetry based on SU3 which relates these. If you want me to state it in the bluntest language, these are all different states of the same particle in some approximate sense. And particularly if you ignore electric charge, because obviously these are distinguished by charge. But if you ignore those things, then they are something like different states of one kind of larger particle. This is very satisfying because it takes a lot of information and packages it into a smaller set. Okay, now it turns out there are many different representations of SU3. The most important ones are the simplest ones. They have dimensions 3, 8, and 10. There's also the singlet, which has dimension 1, which I'll also come to later. What Gell-Mann noticed, again, both of them, but I know Gell-Mann's work better, is that all these new mesons and baryons, 8 of them we already accounted for. The remaining ones fitted nicely, some into the 8, some into the 10, but there were some gaps. That is, in some places, we had 7 particles which fitted into the 8-dimensional hexagon, but there was no particle in the 8th place. In the case of 10, I'll show you the picture. There were 9 particles known, but 1 particle was not there. So one vertex of this 10-point diagram was empty. And basically he said, look, this can't be. If SU3 is a symmetry, this is an irreducible representation. Either there has to be a particle associated to every vertex, or it's not a symmetry. Let's assume it's a symmetry, then there must be a new particle. And this is how he ended up predicting particles. In particular, I'll show you on the next page the meson octet. Earlier, what I showed you is called the baryon octet. It had neutrons and protons. The meson octet had 3 pions and 4 k-mesons, 7 particles. And Gell-Mann wrote, the most clear-cut new prediction for the pseudoscalar meson is the existence of chi0, which should decay into 2 photons unless it is heavy enough to yield pi plus plus pi minus plus photon. Okay, he worked out all this based on SU3 symmetry, and this chi0 now is known as the Eta, and it was discovered. By a stroke of luck, it was discovered the same year. He predicted this in early 61, and in late 61, the discovery of the Eta meson was announced. And indeed, it decayed into 2 photons, and it also decayed into pi plus pi minus and a photon. It had all the properties Gell-Mann predicted, but now was a real physical living particle, which was predicted by SU3 symmetry. Now, unfortunately, Gell-Mann did not really get much credit for this, because that thing I showed you was not yet published. And it was 1961 in the same year, and news traveled very slowly in those days. So people who discovered it weren't quite clear that it was an unambiguous prediction of this Gell-Mann's SU3 symmetry. So in 1962, Gell-Mann said, okay, now I'll do it again. So he grouped a set of baryons into a decuplet, 10-dimensional representation, and he found one missing. And this one was really unknown, and he said loudly, by this time Gell-Mann had quite a reputation, he said, look, there's a 10th particle and the experimentalists better find it. Please go look for it. And he said, I'm telling you what its properties are. It's called Omega baryon, of course, is just a name. He said it will have strangeness -3, it will have electric charge -1, and its mass will be in the ballpark of 1680 MeV. And they found it in 1964. And this time it was 2 years between the time he said it and the time they found it. And now the community was like, yeah, he really did predict it, because, for 2 years, people actually looked for it, and they looked for it because he told them what to look for. These 3 properties and some decay modes, which he also wrote down, told people what they should look for, and they found it. So here I'll summarize. This is the meson octet. The Eta sits in as one of the 2 dots in the center, and it was not seen before 1961, and Gell-Mann predicted it. The omega minus sits at this vertex of this triangle. So you see this triangle has 4, 3, 2, and 1 particle, but 4 was known, the deltas were known, sigma stars were known, the psi stars were known, and only poor omega was missing, and he got it. And this is sort of the key. So these are all baryons of spin 3/2. So these 2 key discoveries came from the proposal of SU3 symmetry. Good. Now let me move on. Often we are taught in the same breath about SU3 symmetry and quarks, but actually there was a logical sequence to it. And it was in 1964 that Gell-Mann made a new proposal, and this proposal was also independently made by Zweig, George Zweig. Again, it was not totally new. There were proposals in the late 50s and early 60s, which were similar, but this was a specific, very concrete proposal. And it said, look, all representations of SU3, mathematicians will tell us, are products of the fundamental representation with itself. That's why it's called fundamental. It's the one that if I keep multiplying with itself, I'll get all the higher dimensional ones. And that one is 3-dimensional. That 3 comes from SU3. So could there be a triplet of fundamental particles in this 3-dimensional representation, and then all hadrons be bound states of them? And so this came from Gell-Mann and independently Zweig. And so they proposed constituents of hadrons, which Gell-Mann called quarks and Zweig called them aces, but the name quark was sufficiently weird. People liked it, so it stuck. And this was the proposal, that there are 3 new particles called quarks: up quark, down quark, and strange quark. Turns out from today's knowledge that's incomplete. There are many more. There are 3 more, but okay. This was the proposal. And he also proposed the electric charges to be plus 2/3, minus 1/3, and minus 1/3 respectively. And the proposal was that, well, baryons, which have spin half, 3/2, etc., are bound states of three of these, any three. So it could be all up, or one up and one down, and one strange, or two downs and a strange. Any way you can combine it. Okay. And there's a mathematical procedure to decompose these products of this triplet representation into irreducible representations, and that should lead to his octet and decuplet. Similarly, mesons should be bound states of a quark and an antiquark. And he gave some evidence that this fits the spectrum of known particles. And today, in fact, we know that this is absolutely true. But I'm jumping ahead. Let me get to what happened next. So there was a new prediction, which is also amusing. If I take quark-antiquark pairs, then there are three types of quarks, three types of antiquarks. So I get 9 objects, U bar, UD bar, US bar, etc. I've listed them. Okay, so there should be 9 particles. But the meson octet had only 8 particles. The 8th one being the eta meson. So SU3 group theory says, well, this set can be decomposed as an octet representation and a singlet, but it does not say that both have to occur in nature. It says that if any of the particles in the octet occur, then the whole octet should occur. And the singlet, well, it could be there, it might not be there. But the quark model broadly predicts that we should have all 9. So there's one combination of these which is not in the octet. Why shouldn't it be there? And interestingly, in 1964, the same year that the quark model of this sort was predicted, a new meson, the eta prime, was discovered. And it has a mass of 950 MeV, which is considerably heavier than these other 8 mesons. And it's exactly the 9th meson. So that was one nice thing. But okay, history is very interesting. Yeah, I see some questions piling up, so I'll come to them. Give me 1 slide or 2 more, and I'll look at the questions. Now, this quark model was met with great skepticism from both theorists and experimentalists, and both groups had the same question. Where are these quarks? You claim there are quarks. Where are they? Why aren't they produced in any experiment? Why don't we see particles of fractional charge? That's the easiest thing to see, because fractional charge, charge is easy to measure in the tracks that the particles leave, and fractional would be really new because we never have seen them before. And the answer went in a bit of a weird direction. A series of experiments where particles were smashed onto protons or neutrons. So this is an incoming proton or neutron. It was hit with an electron, say, which sends, if you like, a powerful beam of energy deep inside. That's the physical picture. That's why it's called deep inelastic scattering. And it smashes this thing up into other hadrons. But in the process, the way in which this photon scatters from inside here and the way in which the scattering appears is consistent not with a soft, squishy proton or neutron, but with something which has literally 3 point-like objects inside it. So that's a very long story, but deep inelastic scattering seemed to reveal exactly the constituents that Gell-Mann and Zweig had proposed. But people refused to call these constituents quarks. Feynman actually invented a new name. He called them partons. Partons for him were the thing that are seen in this experiment. Quarks was some fancy thing that somebody using some mathematics has proposed. And for years, there were papers describing the experimental behavior of partons without mentioning quarks, until it was finally accepted, as we know today, that partons and quarks are the same thing. Well, there are also gluons, so it's a longer story, but certainly some of the partons are quarks. And this is from Feynman's paper, where he said, I call the fundamental bare particles of my underlying field theory partons, and he never mentions quarks in that paper. In a later paper, this is an amusing discussion between ECG Sudarshan and Feynman. Sudarshan said, could it be that partons are like the ether for light waves, that they are like vibrations they're like vibrations in ether and they may not be real? And Feynman said, yeah, even ether was not real. Maybe partons are also non-existent. So it's like just a mathematical structure to explain some experiment, but they are not real in the way that other particles are real. Well, it was nice. It's nice to see this discussion because they were off on, I think, a completely wrong direction. What we know now is that partons, which are also quarks, are confined by the strong interactions, and that's why we don't see them. But they are absolutely real inside protons, neutrons, and all other hadrons. You can go inside and see them. You can't bring them out. That's the bottom line. Okay. So I think it's time for me to look into some questions. There are several now. Let's see what we can do. Good.
Yeah, starting from origin of charge.
Yeah, origin of charge, I don't really have anything intelligent to say. We don't know what is the origin. Fundamental particles have charge. Strangeness, okay, I could tell you, but I think it would take us a little far afield. You know, for this, I'll advise you to read up a little bit of, some textbook or even some popular book. It was a quantum number that was approximately conserved, and it explained why certain particles decay in a certain way and not in another way. Okay, so it was like an ad hoc quantum number assigned to particles to explain certain experiments. And that's how it was assigned. It was not measured directly. It was assigned based on what interactions the particles undergo and what interactions they don't undergo. Okay, SU3, why does SU3 have only 3, 8, and 10 dimensional? No. It has infinitely many irreducible representations. Beyond 10, there's 15, there are all kinds of representations, but these are the lowest ones. Okay, so what your question might be, why don't we have baryons and mesons filling up all the representations up to infinity? I think the thinking is that they might exist, they could exist, but they would be so unstable. You know, even each of these baryons and mesons, almost all were unstable. The higher the dimension of the representation, probably the more unstable it will be. So that's the point. It's not that there are only these representations. Okay, next question. How far should we take the idea of particles falling into some sort of representation of a group? Should we expect all particles which exist to fall under something or draw a line somewhere? So it's not about drawing a line. We have data. In this situation, we had data. Do we have an explanation which is better than saying, I don't know why there are 200 mesons and baryons? Okay, so of course you could say that there's no symmetry group. You could say that all particles are singlets of the symmetry group, which is same as saying there's no symmetry group. But by saying that, you would have explained nothing. By saying this, you explained something and you predicted something. And this is the job of theoretical physics, to explain and to predict. These are the two jobs. So we don't draw a line anywhere. We just look for the best possible explanation. Now, since there are a lot of bright students here, let me say that in the end, this SU3 is not a very important symmetry of the modern theory of particle physics. It's an approximate global symmetry broken by the masses of the quarks. That's why all the particles in these multiplets don't really have the same mass. But there are exact symmetries in nature, and under those, the particles really have identical behavior. For example, the symmetry which sends a particle to an antiparticle called CPT literally means that they have to have exactly the same mass and exactly opposite charge, not approximate. So this was an approximate symmetry, but it led to a lot of progress because it explained things that previously people didn't have any explanation for. So that's the point. It's not that we expect all particles to fall under something, but if there's a symmetry, it simplifies our classification of the large number of particles seen in nature. Why don't the quark and anti-quark annihilate each other is an interesting question. So two things. First of all, for example, a pi plus meson is a U and D bar. U and D bar cannot annihilate each other because they are not antiparticle of each other. But pi 0 has U bar and D bar. It's a combination of these. Okay. And now why those don't annihilate each other is a bit tricky. It's because there's a stable bound state. Of course, in the end, they do annihilate. I mean, finally, the pi naught decays into photons. That's exactly the process where the quark and antiquark do annihilate each other, but it's a stable enough bound state that it has a lifetime long enough that we can detect it and measure it before it decays. So yeah, ultimately those mesons which have the quark and the same antiquark in it, they do annihilate each other eventually. That's true of pi 0, it's true of eta, it's true of eta prime, all are highly unstable. Okay, good. Now, strangeness, comes from the fact that a strange quark is present. Why don't we have charmness or topness? Actually, we do have charmness. We don't have topness. It's an interesting distinction. We have charmness and bottomness, but we don't have topness. So we simply don't use that ness word anymore, but we have charmed mesons and baryons, okay, which carry the charm quantum number, which means they have one charmed particle in them. For example, just like the strange lambda baryon, lambda hyperon as it was called, which is UDS, there's a charm version UDC, and it's called lambda C. So it's like the charmed version of lambda. It does exist, okay. You can have bottomness by the same token. The top quark is very, very strange because it's so unstable that it decays before it has time to bind into any bound state. So alone among 6 types of quarks, the top quark doesn't form a bound state. All the other quarks form a bound state which then decays, but the top quark is just so unstable. It's much heavier, by the way, than all the others. It's so incredibly unstable and so short-lived that the time scale during which strong interactions would have bound it is too long, and by that time the top has decayed. So actually we do have charmness and bottomness. They are there. They are all only approximately conserved, but they are there. Okay, I think I've answered all these questions.
Yeah, so if you don't mind, there are also equally number of questions piling up on YouTube, but I will take just one question. I'll leave others. Maybe if you have time, you can answer at the end. Yeah. This is Anish Acharya says, sir, gluon is massless and carrier of strong interaction, which is short-ranged. Photon is also massless, but it has infinite range of electromagnetic interaction. Why the range of gluon is short?
I can answer this easily, though it's not strictly related to my talk. The reason is confinement. So because gluons and quarks are confined, the strong force is such that as soon as you try to separate any gluons or quarks from each other, the strong force acts like a rubber band and pulls them back together. Because it does that, the gluons can never be liberated. Okay, so we don't even really have a clear statement what is the mass of a gluon. There are no free gluons, so you can't ask what is its mass. You can say that it's massless in the formal description of the theory, or you can say it's effectively massless when it's inside a proton. It rattles around inside the proton as if it was massless, but it's not a true massless particle, unlike the photon. So that because of confinement, quarks and gluons never get outside their own bound states, and that's why the strong interaction is short-ranged. It's short-ranged because what we see is only the residual strong interaction leaking out of the walls of a proton and neutron, which, for example, bind into nuclei. It's actually a weak form of the strong interaction, a weaker form. It's a bit, you might think, like the dipole moment or multiple moments of electromagnetism. So if I have a neutral object, it still has an electric field, but much weaker than the field of each of the objects because the net charge is cancelled. So it's a little bit like that.
Okay, yeah.
Okay, good. So now we get to the Higgs, which is essentially the last topic. And I'm sure you heard this hundreds of times, so I'll just tell you once more in my way of looking at it. Now, the weak nuclear interaction is responsible for, sorry for the typo, responsible for beta decay. And it is a short-range interaction. This one is short-range genuinely. There's no confinement here. And the question from the 1950s was, what is the force carrier of this interaction? Now, on various grounds, it was expected to be a particle of spin 1, much like the photon, but there was a problem in postulating a carrier of weak interactions which had spin 1. The formalism for that is called gauge theory or Yang-Mills theory, But that formalism requires all these spin 1 particles to be massless, otherwise consistency of the theory breaks down. So there's a theoretical objection. And of course, these were theorists like Schwinger, who spent a lot of time even in the 1950s worrying about this question. Now, the range of an interaction is related to the mass of its force carrier by an inverse relation. R is proportional to 1 by m. And because R is small in weak interactions, it's actually around 10 to the minus 16 to 10 to the minus 18 meters. And therefore, m has to be pretty large. Okay, so certainly you cannot have a massless spin 1 particle. So what should you do? Now, it's interesting that here, let me first say that a lot of people like Yang and Lee, really brilliant people, were working on other aspects of particle physics, and they also worked on this question, but they approached these questions from an experimental side. And it turned out that in this particular case, experimental side was not the way that would give you the insight where to go next. It was actually two of the leading theorists of those times, Julian Schwinger and Philip Anderson, sorry, who passed away quite recently, who wrote these seminal papers, and you can see that they have almost the same title. Schwinger wrote Gauge Invariance and Mass, and 1 year later, Anderson wrote Plasmons, Gauge Invariance and Mass. And Schwinger set up some criteria saying that maybe in a certain situation, these massless vector particles, spin 1 particles, could behave effectively massive. And Anderson said, yes, they will in a plasma. Now, of course, nature is not a plasma. So in fact, Anderson's paper ends by saying, look, I have found how massless particle behaves massive in a plasma. Nature is not a plasma, but maybe somebody will understand that nature is some kind of plasma after all. For Anderson, plasma was really a plasma, with particles in it and, a certain state of matter. But he gave this mechanism, and it's a beautiful paper, and it's motivated. Look at its title. It's motivated by Schwinger's paper. It came a year after Schwinger, and even though Anderson was a condensed matter physicist who for much of his life was very negative about particle physics, this paper was written to solve a problem in particle physics, not to solve a problem in condensed matter physics. As it turned out, it had implications for both the subjects. Following upon this came these two papers in 1964 by Ongler and Brout first, and then just a little while later by Higgs, where they did not seem to be aware of these previous papers. In particular, they weren't aware, I think, of the paper of Anderson, though it was actually 2 years old by then. And they proposed a mechanism how in explicit models, but only toy models, not realistic models, how a massless particle via the mechanism of spontaneous breaking of symmetry can acquire a mass. And the idea is today called the Higgs mechanism, although it should be named after all these people. Two of them got a Nobel Prize, Ongler and Higgs, but then Brout was no more, unfortunately. Otherwise, all three would have got it. But the idea actually is not that far from Anderson's plasma, except that it's not electrons that make a plasma. Here it is a quantum field. It's a very abstract plasma. It condenses to form a kind of quantum soup. And it's it's something we can explain in mathematics with equations. But physically, we don't really know what this means because the soup is already around us. We live in that soup. The vacuum is that soup. Okay. And this soup is such that the force carrier of weak interactions, which wants to be massless because theory makes it so, as well as all weakly interacting particles, in fact, essentially all particles in nature acquire a mass as they propagate through this soup. So Higgs and Ongler gave Brout gave the mechanism, Anderson and before him Schwinger gave the sort of conceptual idea. And interestingly, even then, from 64 to 67, nothing of really major importance happened. So here's my picture of the Higgs soup and a particle sort of passing through it. Note, by the way, that the Higgs soup does not correspond to any particle. It's only a soup. But in suitable models, when you form this soup, a spinless particle is left over, and it's that which is called the Higgs particle. So it's not the soup that is the Higgs particle. Often there's a confusion. There's a soup and a Higgs particle. Both come together. And Weinberg, in particular in 1967, made a model of the weak interactions that incorporates the Higgs mechanism in great detail, and which is proposed as a realistic model of the weak interactions, which moreover unified them with the electromagnetic interactions. That aspect I haven't focused on here. Sheldon Glashow had already talked about unifying electromagnetic and weak interactions. Abdus Salam had already had similar ideas in the same period. And these three people came up with essentially what today we call the standard model. And it's a marvel that actually the model has changed very little from what they proposed. If you take Weinberg's paper in particular, you can paste his equation for the model into a modern textbook, and it's still the right equation of the standard model. And these three people got a Nobel Prize for their proposal in 1979. Okay, now their model had some precise predictions, and you may be surprised because these precise predictions had not been verified in 1979 directly. So they predicted that there are three carriers of weak interactions. Two of them are charged. Sorry, I wrote it wrong. There are three spin 1 carriers of the weak interactions, W plus minus, which are charged, and Z, which is neutral. Sorry for the typo, I put charged in the wrong place. Their model predicted not only that there are three, but also the range of their masses. So it was a clear directive to experimentalists where to go and what to look for. Unfortunately, there was no accelerator at the time that could go there and look for that. It had to be built. They also predicted a neutral, uncharged, that is, spinless particle left over from the Higgs mechanism, the Higgs particle, but the mass of this they could not predict. It was left in a very wide range because it depended on one more parameter in their model, which was not constrained. Now, in the mid-70s, there were indirect detections of these first two, I've called it two, W and Z, particularly Z, which is very striking. This is called weak neutral current. And this is why they got the Nobel Prize in '69. It was felt that this indirect detection was good enough to ensure that these particles exist. But it was only in 1983 that the W plus minus and Z were directly produced, discovered, measured, and of course their masses lie at the top end of this predicted range. Higgs took a lot of time more because partly because its mass could not be predicted, partly for just other reasons. You know, experimentalists cannot always find just what is predicted because the sensitivity of the experiment has to be tuned for certain things. They have to know what to look for. And it took till 2000, not 10, but 12. Sorry, that's another typo. I should correct a few typos here. In 2012, the Higgs detection was announced. Okay, and here's this beautiful graphic that CERN produced for us to marvel at the production of the Higgs particle. Okay, so that concludes the main part of my talk, and I only need 5 more minutes. I'm a bit over time though, but I hope I have 5 minutes.
No problem, Sunil.
Okay, so this is the point when I can answer maybe a question which I'm seeing here, which says, what is so special about weak interaction that it has 3 force carriers, unlike that of other two have only one R? So I forgot, I didn't talk about gluons. There's not one gluon. The gluons are in the 8 representation of SU3. So there are 8 gluons. The photon is in a representation of U1, and U1 is a group which has only one-dimensional representations. And the W and Z, it's a little more complicated, but essentially they are in the triplet representation of SU2. And so the rule is that the gauge groups are U1, SU2, SU3, and the force carriers are always in the adjoint representation of these, which are of dimension 1, 3, and 8. A new little twist is that the 1 of U1 and the 3 of SU2 got mixed. And so the photon is one combination of the SU2 boson and the U1 boson, and the Z is a different combination of those two. So there's some mixing. That's why what we call electroweak unification. But It's not special only about weak interaction. Gluons, there are 8 gluons. And the way we think of 8 gluons is in terms of color, anti-color pairs. They're not, gluons are not made of color, anti-color, but they're classified by an index which is color, anti-color. But that's a subject for another, yeah. Okay, where are we heading? You know, I'm definitely not the expert here to answer where we are heading. I will give you my thoughts, whatever they are on the last slide. But I will request you to ask qualified experimentalists and phenomenologists, of which there are few in the audience and many in India, to tell us where we are heading. I'm really not good at that. I've done this exercise, which I hope you found interesting, to look at some summary data and just think. You know, sometimes we should think without jumping to any conclusion. I like to do that. And so here is one table which I just made. I made it today, actually. From prediction to detection, how long did it take? So I've given in the first column the name of the particle. These are all particles I've discussed today. In the second column, the year of the prediction, although it was a bit fuzzy in some cases. For example, Dirac didn't really propose positron in 1928. He really proposed it in 1931. The Higgs didn't really propose the Higgs boson at all. He proposed something in a toy model. The real Higgs boson was proposed by Glashow, Salam, and Weinberg in 67. So there's a range, but whatever. Look at the last column. It took, depending how you count, 1 to 3 years for the positron to be discovered, 25 long years for the neutrino to be discovered, during which, by the way, all kind of people were mocking Pauli about his crazy idea, but they didn't have a better one, I should say. Less than a year for Eta meson, 2 years for Omega baryon, 4 years for quarks in deep inelastic scattering, but it took another maybe 6 or 8 years for people to understand that deep inelastic scattering had seen quarks. W boson direct took 16 years, indirect took something more like about 6 or 7 years. Z boson the same, and Higgs boson took the longest ever, 45 to 48 years. It's quite amazing. What, however, is true is that in every case in this table, the boson or the particle that was found was really the particle that was predicted. It's not that we have to use some imagination and say that, well, this neutrino that is found was roughly what Pauli had in mind. No, it is a spin half particle, it's neutral, it carries lepton number, it is produced in beta decay, it fulfills everything that Pauli said and more. Of course, we know much more because of experiments, but it is really what Pauli said. The positron is really what Dirac said in 1931 with Oppenheimer's help. The first time he had it wrong, but second time he had it right. Eta and Omega are exactly what Gell-Mann said. Quarks are exactly what Gell-Mann and Zweig said. W and Z and Higgs are all exactly what Glashow, Salam, and Weinberg said. So I want to emphasize the point that it took a long time, but the reasons to propose them were good, and they are there because in some sense they had to be there. Of course, they might not have been found. There may be other predictions which have gone bad. I don't know. People should talk about those. People more expert than me. Now, two things. Acceptance can be slow. Here is something by a sociologist of science who wrote a very nice paper. He said in the 3-year period following positrons, Dirac's equation was discussed in 72 papers that did not mention the positron, and the positron was discussed in 63 papers that did not mention Dirac's equation. So you can see here, people looking at the experiments didn't want to believe that there was a theory. People looking at the theory didn't want to believe there was an experiment. Not didn't want, they were somehow not able to merge the miracle that the reality of the theory and the reality of experiment were one and the same reality. Feynman, in his first paper on partron model, doesn't mention quarks and doesn't even mention Gell-Mann, who he knew very well. Okay. He mentions it eventually only to shoot down the idea, and that also he mentions not Gell-Mann but Paskos, and says, well, he thinks that partrons are quarks, but I don't think it is, and so on. In the same thing where I showed you a discussion between Feynman and Sudarshan, there was also a discussion on whether partrons can be quarks, and he sort of poo-pooed the idea. So acceptance takes a long time. Physicists often lack patience, and here is one person who, although he gave us a lot of great things and he was a very fine person, but he criticized Einstein's proposal of light quanta. He discouraged Dirac in his search for quantum mechanical equations, saying, well, there's already Klein-Gordon equation. Why do you need Dirac equation? He opposed Pauli's idea of an invisible neutrino. He ridiculed Yukawa's theories of mesons. He disparaged Feynman's approach to QED. Now, probably he was there for a reason. We need some critic who is intelligent but has a critical faculty to guide us from going too much astray. Okay. Journalists also have impatience, and that is increasing now. This I quote because I think it's the stupidest headline I've ever seen about physics in my life. This is 2011 August. Higgs boson is running out of places to hide. So you imagine that the Higgs boson is a person who's trying desperately to hide from people who are searching for it. And we've covered all the places that it could be. And, you know, it's trying to hide, but we are going to figure out eventually that it's just not there. And by the way, not only this journalist, but a lot of my colleagues, even at TIFR, were telling me right until 2011, oh, it will never be found. The point here is, oh, it will never be found is good. But the convincing theory, what replaces it, how masses are given to vector particles, was not there. I mean, there was no better theory. People tried many theories. All the other theories were worse, and they were wrong. So this is another lesson that we learn. This lesson is about both journalists and general impatience. Okay, and this is my last slide. We are looking today for supersymmetric particles at the Large Hadron Collider. And the idea is that for all the particles we know, there's a shadow world of much heavier supersymmetric particles, one for each particle. Just like earlier, there was one antiparticle for each particle. At that time also, the number of particles doubled. This will also double the number of particles. This prediction is worth a full talk, and not by me. There are many people, by the way, in India working on this search. Particularly, I want to mention in my own group over here at IISER, Saurabh Dubey and Seema Sharma are two people who work on the CMS collaboration actively. There are many at TIFR, there are many elsewhere, there are probably some in the audience. But these days, there's a tendency both for journalists and students and sometimes faculty and researchers to believe the search is over and it has failed. Maybe it has. Maybe we can't be lucky always. Or maybe it isn't over. I'm told it's not over. So this is a thought I'll leave you with. And this is part of the reason I compiled all this information in one talk to give you an idea how theoretical prediction and experimental detection match each other very well in the end, but we don't know where the end is. And we probably are not there as yet. So with that, I'll stop. Thank you very much.
Thank you very much, Sunil. That's really fantastic talk. As you rightly put in, so many kind of compilation of so many, let us say, the problems, but the way people looked at eventually the way they have been discovered. At the same time, there also, of course, an unfinished agenda that is actually open for more younger audience, to your audience today. But I'm sure there are some more probably questions. If you can take a couple of them, let us say before 7:30, we'll take that as a hard close.
I'm very happy. Yeah, I'm happy. I'm here till 7:30. Surely.
Okay. Let me just simply go to YouTube and take a few questions, maybe from the end.
I think Vivek also has raised his hand, but you can get YouTube questions and maybe we'll come back to Vivek.
Okay, fine. That's fine. So one question, Sadas Sahu says, last lecture by Professor Rajaji mentioned there is a model where integer electric charge of quarks are taken care. Why only fractional charge model is popular over integer charge model?
Yeah, indeed, that's very important. Rajaji himself worked on the integer charge model, and there's a long history. So if it was a talk on the quark model, I would have gone through that history. The fact is that this proposal with fractional charge is confirmed by experiment, including the fractional charge. Okay, the number 1/3 or 2/3, actually it's square. You can actually plot an experimental quantity and measure some coefficient from it, which comes out to be 4/9, which is the square of the charge of the up quark. So it's actually confirmed in detail by experiment. That's the reason I did that. I really should have, I really apologize that in this talk, which already went over time, I couldn't fit in the history of the quark model proposal, but it's an important one.
Can I make a point, please?
Please.
Yes, Rajaji.
Can I add something?
Yes,
Please.
Rajaji.
Yeah, this integer charged quark model is a little older than the Gelman-Zweig fractional charged quark model. It was due to Hahn and Nambu, although they did not gauge it fully. And when we gauged it and constructed the full Yang-Mills gauge theory of integer charged Hahn-Nambu quarks, one important thing we discovered, there is Prabir Roy and myself, in 1975. We discovered that although the quarks are maybe integer charge, they will exhibit only the fractional charge in all deep NLSC experiments. Sunil is mentioning the experimental support of fractional charge for deep NLSC experiments. As seen by a high Q-square deep NLSC probe, the quarks manifest only the fractional charge. This we proved long ago. And hence, even fractional charge, integer charge quark model are still viable. But the only thing one must say is the fractional charge quark model is much simpler, and most probably nature follows that. But there is no experimental proof of that. In contrast to integer charge quark model.
Thank you.
Thanks, Rajaji. Sunil, you could see that there are more questions coming up. Before that, you said Vivek, Prastathar's question. Let us take him.
Well, it's not a question really. I just wanted to make a comment. When Sunil referred to neutrinos, we still do not know whether the neutrino is its own antiparticle. And if it turns out that it is its own antiparticle, then of course the beta decay would be emitting right-handed, helicity neutrinos and vice versa for the beta plus decays. It's just a comment.
This is of course
we
true.
do not.
But I think, Vivek, we know that at least some neutrino is not its own antiparticle, right?
No. We do not yet know. If, for instance, if neutrinoless double beta decay is seen, then we know that it's its own antiparticle.
No, but there are three flavors of neutrinos, right?
No, flavors is different. Flavors is different.
I'm asking,
I'm saying particle, antiparticle. But that may not be so in the case of neutrino.
The question is it consistent with experiment that all of nu e, nu mu, and nu tau are their own antiparticles or are Majorana particles?
I mean, if we find neutrinoless, maybe, okay, Rajaji wants to interject.
As of now, it is quite consistent to say that they are all Majorana particles. Only neutrinoless double beta decay will prove it, but we do not know as of now whether neutrinos are Dirac particles or Majorana particles. Both possibilities are open.
Well, the possibility is also that some are Majorana and some are Dirac, right?
That will be very difficult because all these three flavors behave exactly alike. So if nu e is Majorana, nu mu and nu tau also have to be Majorana. Otherwise, it will be there will be theoretical inconsistency.
I see. Okay.
Okay.
I'm not sure why, because they are all anyway weak interaction SU2 singlets. So what would be the inconsistency?
Because there is a generation symmetry. Nu e, nu mu, nu tau belong to three generations, and there is a generation symmetry having electron, muon, and tau as three members of one symmetry. If that is true, the corresponding neutrinos also have to be exactly.
That I agree, but we don't know that generation.
We don't know. I am only making a theoretical point.
I still think experimentally it's an open question.
It's a completely open thing. Nu e may be Majorana and nu mu, nu tau may be Dirac or vice versa. That possibility exists experimentally. Only neutrinoless double beta decay will completely solve the problem, but they have not seen it yet. Neutrinoless double beta decay has not been seen.
Yeah, Sunil, I think there are quite a few questions on YouTube. I'm not sure you'll be able to cover them all. I feel sorry about that, but at least let me take just one question if possible. Sulagna Bhattacharya, sir, kindly clear the concept of Higgs soup. I mean, what is it consist of? Thanks for your beautiful session. So maybe one or two more words on it.
So unfortunately, this can't be cleared without doing the equations. Higgs soup is like a metaphor but let me just say these words. There's a Higgs field. It's a scalar field, and it has a constant value throughout the universe, which is non-zero. Okay, that's what we call the Higgs soup. So it would be, if you take an analog, imagine the electromagnetic field. Certainly the universe doesn't have a constant electromagnetic field everywhere in it, right? But imagine a universe which did have such a constant field everywhere. Okay, now an analog of that, but coming not from photons, but coming from a spinless particle, analog of such a constant field everywhere in the universe would be the Higgs. And it's not directly measurable because we don't have any universe in which that soup is not there. So we have nothing to compare with. We can't say that, well, we are going to measure the Higgs, the vacuum with Higgs in it and vacuum without Higgs soup in it, and we'll find some difference. If we could, we would find a difference. But the vacuum without Higgs soup doesn't exist anywhere in the universe now. It may have existed in the very early universe. So unfortunately, there's really no simple way. This is why Higgs mechanism is a notoriously difficult and subtle concept, which is best learned by studying quantum field theory, which of course I advise all students to aim for eventually.
Something related possibly, maybe, and then we still have one more minute before 7:30. I had a question. Do we understand the mechanism of the spontaneous symmetry breaking discussed? Can we look for answers in the quantum fluctuations in the early universe?
Yeah, I see this in the Zoom chat from Kaustubh Gupta. So I don't know what understand the mechanism means. We can actually write a theory. We can write equations which do have the feature of spontaneous symmetry breaking and which give rise to the Higgs soup. That's the kind of equation that Higgs and Ongler and Braut wrote already in '64. And then Glashow, Salam, and Weinberg again had by 1967. So the equations are well known. Mechanism is a much deeper question, like why is it there? Those are much deeper level why questions. And early universe, quantum fluctuations in the early universe, my understanding is that they're supposed to tell us more about gravity and about about the inflation itself or something. But I don't know what it tells us about spontaneous symmetry breaking specifically, except that at some time when the temperature was very high, it was not there. And the way to think of that is, if I'm in a soup and I'm at very high temperature, I might not notice that I'm in a soup because I'm already being bombarded by lots of very high energy particles. It's only when the temperature comes below the average energy, or if you like, the average scale of that soup, that the soup starts to have an effect on me. So early universe, a phase when things were very hot, is the time when we can understand the soupless phase of the universe. And then when the universe cooled, then the soup became relevant to physics. That's the way people describe it.
Okay. Sorry, Sunil, but at least please take one question because, okay.
I have no problem.
Okay, so this is Rupak Majumdar. So beta particle is a quantum particle, and what does energy and momentum conservation means there? And how then this led to neutrino?
Oh, beta particle, of course, is nothing but our friend the electron. And energy and momentum absolutely have a meaning in quantum theory. They are operators with eigenstates and eigenvalues. So in a decay process, the outgoing particles are produced in wave packets, and wave packets have an approximate position as well as an approximate momentum, and the uncertainty of both is as low as it can be, roughly, and it's very low, I mean, from an experimental point of view. So, you should realize for students that nothing is ever produced in a position eigenstate when its momentum is totally uncertain, nor in a momentum eigenstate where its position is uncertain. Okay, everything in real experiments is produced in a wave packet. So a wave packet has energy, has momentum, and it also has a spread, a very narrow spread of energy and momentum. So when we say that the electron carries away some energy or momentum and we measure it, there's always a spread, even given by quantum mechanics. but the experimental uncertainty is typically larger than that. So we don't have to worry about it. So yeah, even quantum particles do have, that's why, you know, the Large Hadron Collider, we say that it's a 14 TeV machine. 14 TeV is the energy of the combined pair of particles going in. But of course, they are not in a momentum eigenstate, because if they were, they would never meet at a point and collide. They are in a wave packet.
Yes, Sunil.
That's not often enough. Huh?
No, I was just saying that thank you very much. I think you are on call for 2 hours now.
I have no problem.
And really went through, and it was one of the probably the most interactive lecture in this series. And we had almost 70 participants on both YouTube and Zoom, and it was very well attended too. Of course, people who know you, they'll definitely will come and attend your talk. And but most importantly, you also put up such a nice material for especially the younger participants to ponder over and also look for exciting times to come, both in the theory as well as the experiment. And I really liked your one of your last few slides where you really mentioned how long it takes really to from theory to actually build an experiment and actually prove, and why people don't have patience. You know, I mean, everybody, journalists, our own colleagues, maybe funding agencies, and so on. But
thank you. If this talk was not public on YouTube, I might have said something about it.
Sorry. Okay. So thank you once again. I also want to take a minute to advertise the next talk in this series. Unfortunately, we don't have a talk planned for Wednesday, which should have been. So the next talk that we have is on Friday on 24th. And Pune Sunil mentioned quite a few times about CMS, about LHC and the experiments there. One of our younger scientists, Professor Josna Komargiris, she is going to talk from Indian Institute of Science, going to talk on a typical particle search at colliders from data to discovery. So it's going to be another very interesting and also interactive lecture. Please come back. But that is on Friday at 6 p.m. No, so we don't have any talk on Wednesday. This Wednesday, we don't have a talk. So please remember that. So once again, on behalf of all of you, I would like to thank Sunil for his excellent talk and also, you know, patiently answering every single question. Thanks, Sunil.
Thank you. It was my pleasure.
Okay. Thank you very much. Bye-bye. Take care and good night to everyone.